In our previous videos, we saw how we can use transistors, Zener diodes, and op-amps together to get a regulated output. We noticed that maximum loss is present at maximum load and maximum input. Hence, if we use a switching element, we can reduce this loss. I am Reshma, and today we will talk about the need for switching regulators. Today, we will learn about switching regulators and its definitions. We have seen that maximum loss is present at maximum load and maximum input when a transistor is used. This loss is mainly because of the voltage drop that occurs across the transistor. If we reduce this voltage drop, then this loss can be reduced. If we operate this transistor in saturation region, that is, the switch is completely turned on, then the voltage drop is almost equal to zero. That means the transistor is either fully turned on or fully turned off and it is operating as a switch. Let us now use a switch in place of a transistor. Let the switch be connected to a resistor in series with it. This is the load resistor. When the switch is turned on, the input voltage is seen across the load. When the switch is turned off, the voltage is 0 volt. If we observe here, the output is not steady. It is a pulsating DC. The average voltage is lesser than the input voltage. It is given as Vout is equal to Vin T on divided by T on plus T off. That is equal to Vin into T on by T total. Let the input voltage be 15 volts. We saw that Vout average is equal to Vin into T on by T total. The term T on by T total is defined as the duty cycle. On substituting this in the previous equation, we get Vout is equal to Vin into D, where D is the duty cycle. For example, if duty cycle is 33%, then the average output voltage is given as 15 volt into 33 by 100, that is roughly equal to 5 volt. Here, the output voltage is pulsating DC. However, we need a steady output. To filter this DC voltage, let us now use a capacitor in parallel to the load. When the switch is on, input voltage appears across the load and the capacitor. The capacitor voltage is now equal to the input voltage. When the switch is turned off, the capacitor acts like a source and supplies voltage to the load. As a result of this, the capacitor voltage decreases exponentially. The rate at which the capacitor voltage decreases is given by the capacitance and the resistor value. When the switch is turned on again, the capacitor now charges to the input voltage. This cycle repeats. Here, the output voltage is still not steady. Using capacitor in parallel to the resistor, make sure that the voltage across the load does not fall to 0 volt when the switch is turned off. In order to get a steady DC output, let us use an inductor in series with the load. Now, when the switch is turned on, the inductor limits the rapid rise of current in the capacitor. This means that the capacitor slowly charges. When the switch is turned off, the current in the inductor starts falling. However, there is no path for discharge. If we add a diode in the circuit, then we can provide a path for the inductor current to freewheel when the switch is turned off. The circuit obtained is called as a buck regulator circuit. In our video today, we saw how we can use an inductor, capacitor and a diode to get a steady DC output. We will learn more about this buck regulator in our subsequent videos. Until then, let's keep exploring and learning. Thank you.